TeMeLu is an application project funded through the INNO4COV-19 Consortium via the European Commission. TeMeLu is an acronym for TeleMedical Lung Monitoring. It was developed to monitor the respiratory health of COVID-19 patients. Emergency care units and observation stations for COVID-19 patients were scarce at peak times of the outbreak. In such a case, prioritization is desperately needed. Moving people into the right place at the right time could relieve some overcrowding situations. If not yet critical patients could be separated from critical patients, then these not yet critical patients could be moved to other locations. Respiratory health monitoring is one measure for identifying critical patients which need urgent attention. It is a warning indicator that when properly used can give 3 to 9 hours of early notification. COVID-19 affects the upper and lower respiratory systems and leads to pneumonia-like symptoms and shortness of breath. This is caused by disease-related drops in blood oxygen levels. As the body tries to compensate the drop in oxygen levels, breathing rates gradually increase. A gradual respiratory rate increase of 50 to 100% is not untypical and looks very different from rapid increases in breathing rate due to physical activity. Eventually, the increased breathing rate can no longer compensate the drop in blood oxygen levels, and the heart rate begins to increase. At this point in time, septic shock is likely to occur in short progression. Septic shock is to be avoided as it could lead to organ damage, which can further complicate treatment. Identifying breathing rate changes as an early indicator of worsening COVID-19 disease progression is a very reliable indicator, giving 3 to 9 hours of pre-warning. Patients can be moved to intensive care units not too early and not too late, making optimal utilization of medical staff and equipment resources possible. TeMeLu is an easy wearable device for monitoring lung and heart functions, which can be given to risk groups and works via telematic monitoring. TeMeLu has achieved technical readiness level 6 to 7, which means it was used for field testing to evaluate the overall performance of this approach. Early detection and antibiotic treatment of sepsis are critical for improving outcomes. Every hour of delayed treatment can be associated with roughly a 4 to 8% increase in mortality. SOFA, which stands for Sequential Organ Failure Assessment, is a score for rating septic shock likelihood. Increased respiratory and heart rates are just 2 factors contributing to the SOFA score. Ultimately, a physician's neurological assessment is needed to round up the patient evaluation. But respiratory and heart rates can be monitored continuously, and the absence of changes is a good indicator of stability. A neck-worn acoustic IoT sensor placed near the artery and windpipe can monitor respiratory and heart rate changes over extended periods of time. The average respiratory rate is between 15 and 18 breaths per minute for an adult, slightly higher for children and even higher for infants. Their respiratory sounds can be easily picked up via stethoscope-like sensors and analyzed. As breathing consists of inhalation and exhalation, the resulting envelope frequencies are half the respiratory rate. When analyzed over several breathing cycles, the periodicity of constant breathing results in very clean spectral frequency peaks. The same is true for heart rate. This information, when plotted over time, gives a very good indication of respiratory and heart rate changes. When coupled with motion sensors, activity-related changes can be filtered out. The goal of TeMeLu is to be easy to use. Anybody should be able to put it on without requiring a specialist or a physician. Therefore, Band-Aid-like solutions were disqualified. Initially, TeMeLu was conceptualized as a wearable vest. However, this approach was eventually eliminated also for being too costly, too size-sensitive, and lacking stable signal performance. Achieving a stable body contact was identified early on as a main challenge. Ultimately, a solution was found via a wearable neck device monitoring the carotid artery on heart rate and the windpipe on respiratory rate. The wearable neck device was developed to achieve field test maturity and enable overall performance evaluation. TeMeLu is based on the scientific foundation of previous research projects into respiratory health. Württemberger and Murphy have shown that a large number of lung diseases can be differentiated via lung auscultation sounds. While lung oscillation sounds and associated diseases are typically linked to specific lung locations, the presence or absence of oscillation signatures is propagated through the windpipe and can be picked up from there. A stethoscope placed on the neck near the windpipe can pick up enough oscillation signatures to differentiate between normal and abnormal patterns, even if some high-end frequency responses are lost. This is adequate for the purpose of pre-diagnostics and early warning. Therefore, neck-based breathing and escalation monitoring near the windpipe is very promising. The neck is easily accessible without having to shed clothes. Determining the best sensing technology and sensor fixation to ensure a reliable signal pickup was a main challenge. Several sensing approaches were investigated. In the end, the reliable and proven stethoscope approach was chosen for picking up oscillation sounds. Initially, commercial stethoscopes were used for concept validation. In subsequent steps, custom designs were developed and tested. The custom designs were more compact and optimized for the chosen neck-based fixation concept. Significant effort was placed into signal amplification and conditioning to ensure a good dynamic response over the full range of breathing patterns from shallow to labored. Next, lab tests were performed to evaluate the breathing frequency response. It is important to note that the base frequency of in and out breathing is identical. The changes are in duration, intensity, and frequency modulation. Two identical base frequencies, separated by a phase shift, still share the same base frequency. There are different approaches to evaluate cyclic patterns. Breathing is a cyclic pattern. When monitored over several respiratory periods, the amplitude of the base frequency becomes more pronounced, and less significant or random events are de-emphasized. This simple approach greatly reduces the analytic computation efforts. Another insight from lab testing showed that both misuse, meaning friction between the sensor and skin, and human-made sounds like speaking, coughing, and swallowing share neither typical frequency or amplitude responses of normal escalation sounds. Therefore, these other sounds are easily differentiable from target signatures. Lab tests also showed that both breathing and heart rate frequencies can be easily determined from a stethoscope placed above the carotid artery and windpipe. The next step was to modify the lab equipment for field testing. For this, a portable device was developed. Field tests focused on determining the effects of motion activity on the signal quality. The same basic concepts of signal evaluation as previously applied to lab tests were applied to field tests. Field testing included sitting, walking, resting, stairs, bicycling, and various activities such as speaking, eating, drinking, and coughing. While motion-based testing showed occasional signal toss due to sensor skin motion, overall the performance matched lab results. Both respiratory and heart rates could be easily identified. While field testing was very promising, a couple of issues did arise which require attention. To clearly differentiate between activity-related respiratory and heart rate changes, a motion sensor shall be added. The neck-based sensor design is suboptimal for resting, as the sensor cup is pushed out of position when lying on the neck. To overcome out-of-position monitoring, multi-point piezo-based surface wave monitoring might be a better approach. These points are quite minor and easy to fix and do not lessen the achievements to date. TeMeLu has achieved its main target and has shown that respiratory and heart rate monitoring via a simple, easy-to-use neck device is possible to effectively detect respiratory and heart rate changes as an input to sepsis SOFA assessment and by that COVID-19 patient prioritization. TeMeLu has shown that its frequency response is only slightly less than chest-based stethoscope examinations. As such, it has a significant potential as a CPOD monitoring device. TeMeLu could also be used to access carotid stenosis. If multi-point piezo-based surface wave monitoring is implemented, not only can characteristic swishing sounds be analyzed, but also differential flow measurements could be made. TeMeLu will be deployed as a research tool for academia and industry. If you would like to download the full report or inquire about TeMeLu for research purposes, please visit our website at www.neurocontrols.io. We would like to thank the INNO4COV-19 Consortium and the European Commission for funding this project.